Hello students, welcome to Unit 1 Notes Section 1.5. We've done a whole bunch of this section, there's just a little bit more to go, so I am making this video to supplement what we missed, what we weren't able to finish in class today. So we did all of this, we talked about domain, range, specifically asymptotes and holes, focus on inverse functions, one-to-one functions. And we left off kind of around here where we talked about natural log being the same as log base e of x, and also the common log being log base 10 of x. And then I asked you, why don't you review this on your own? Let me know if you have any questions on it. Just different properties for inverse functions and for logarithms. So I'm going to do a couple examples of this. For instance, if I had e to the x equals 5, and I asked you to solve for x, you would perform the ln operation to both sides. And what that would do is wipe out your ln of e, because it's the inverse function, right? So ln of e goes away, x would drop down and out front in terms of multiplication, but ln of e becomes 1, so it's x times 1 equals ln of 5. So that would be one way to solve it. And then let's go back in a different direction. So what if I wanted to remove an ln, for instance? So let me switch these around. I'll keep this one here. But what if I had, trying to think here. Let's say I had the ln of x equals 5 instead. Well, how would I fix this one? It's really cool. The ln of e inverses each other, but in this case, you can also do an inverse here. It's called exponentiating a function. So if ln of x equals 5, then e to the ln of x equals e to the 5. I can create a base here, and what's cool about this is these go away, and I have x equals e to the 5. So you can actually solve for what would work using the inverses here. And that's what this pretty much says, your inverse properties. All right, you should be familiar with your logarithmic properties and then change a base. We quickly went over in class. So let's solve here for x. Let's start with this one. This one's probably going to be a little bit easier, b. We are going to do the ln of both sides. And the ln of both sides will get me, this will get knocked out here. The 2x drops down to the front in the meantime. So that happened first before we even found the ln of e. Well, no, it happens at the same time, I'm sorry. And this is equal to the ln of 10. Whoops. And then we're going to divide both sides by 2. And so x is equal to the ln of 10 over 2. And that can't be simplified. That is a number. You know what? I can approximate it. Let me approximate ln of 10 over 2. So the ln of 10 all divided by 2 is 1.151. 1.151. Whoops. So x equals that, but x also approximately equals 1.151. Is that what I got? Yep. And there we go. All right, solve for x in this one. Well, I'm going to follow what I showed you earlier. The way to undo an ln is to work with e, but we can't put e on the inside because it's not a possible thing to do. But what we can do is we can create a base e on both sides. And with that base e on both sides, what I do is I exponentiate. This is called exponentiating my function. So e to the ln of x is just x. And then on the other side, I have e to the 3t plus 5 as a whole. And I'm done. I've already solved for x. Okay? Exponentiating. Let's do this one in a different way. Remember when I had log base 2 of 8, and I asked you what that equals, and you said, oh, it's got to equal 3, because 2 to the third power equals 8, right? I said it's kind of like, I call it the circle of life. But here we are, 2 cubed is 8. The same thing is actually happening here. So we have log base e, well, it's ln. Let's call it ln of x equals 3t plus 5. So if I rewrite this as log base e of x equals 3t plus 5, I can do the same exact thing I did here in green. I can do e to this power equals x. So e to the 3t plus 5 equals x. So you can do either method here. You're going to end up with the same thing. X equals e to the 3t plus 5. And you know what? I'll just, whoops. I will put this in parentheses. Okay, that's that one. Now, graphing a base, what am I doing here? We don't really, graphing a base A logarithmic. Okay, all I want to show you here is, as that base changes, it's gonna get greater. That's all. Log base 2 of x, right? Log base 2 of x. Instead of me graphing log base 2 of x, I'm gonna graph log base, let's see if it'll let me do d of x and put a slider in. I don't know, I've never tried a slider this way, but, oh, it will work. Okay, so there we go. So as it increases, oh, okay, well, it can't be negative, right? So that explains d, we can't have a log base of a negative number. So let me change this to be 0 to 10. And I'm going to start at, I'm going to go a little bit slower. I'll only move forward, okay? See what happens. So it starts off, and when it's lesser than 1, it's going downward, because remember, it's going to be a fractional exponent. Think about d to what power would be x, and if d is a number lesser than 1, then it's going to be moving downward. But let's say let's start at, I really don't want to start, I think I just want to start at 1. So you see here that the greater number I'm given for d, the lesser of a power I'm going to need to get that same value, which is why that's getting closer to being horizontal. All right, so graphing a base A logarithmic function. I guess the important thing here is that there's an asymptote here, you cannot graph a negative number, and we just saw that. So let's put the question in focus here. There, that's your asymptote right there. All right, and so your domain is going to be all real numbers greater than 0, and your range is going to be all real numbers. We can say there's no holes. There's an asymptote. There's a vertical asymptote at x equals 0. All right. Finding time. Sarah invests $1,000 in an account that earns 5.25% interest compounded annually. How long will it take the account to reach $2,500? So I have $1,000 as an investment, and we have a rate of 5%. So remember, this looks like 1.0525. So 1.052. Let me erase this. 1.0525 to the time. And the question is, when will that equal the amount that I want, which is $2,500? So I want whatever the $1,000, what do I need to invest it for it to increase 2.5 times what it's going to? So the first thing I'm going to do is I'm going to divide both sides by 1,000. And I get 2.5, because I want it to be 2.5 times what I had. And I have 1.0525, whoops, t. Now at this point, you can log base both sides. So I'm going to log, but you know what I'm going to do? I'm going to do log base, no, I'm just going to log both sides, 2.5. Because remember, I could do this base right here. If I did that base, it would work out perfect. I would just have t on one side, but I'll just do one extra step. So I'm going to log base 1.0525 to the t. The t will drop down, and I have log base 1.0525 on this side, and I have log base 2.5 on this side. I divide both sides, so t is approximately equal, t is equal to log of 2.5 over log of 1.0525, and 1.0525, okay. And it's going to be about 17.907. 17.907 years. Because I compounded it annually. That's years. Okay? Now again, I could have log based, if I wanted to, I could have log based 1.0525 both sides, which would have been kind of weird, of 2.5, and I could have log 1.0525 to the 1.0525t. Yikes, here, let me move all this stuff over. I could have done this, and then I would have just had, this is really weird. So we don't normally do this, but we can. Oops, to the t. And then, boom, this goes away, and you have just t. And you have this on the side, log base 1.0525 of 2.5. That would have worked as well. So I'm just going to put it in just to show you. We're in projector mode. Okay. Whoops. Again, you don't have to do this, but I just want to show you it is exactly the same. Okay. All right. Alternate way. Okay, this is kind of where we did leave off. For this function, we addressed all of the vertical asymptotes, the holes, the horizontal asymptotes, domain range, and end behavior. Notice your end behavior literally is what you're pulling from your domain or range. As you approach those numbers, y is doing something. All right, so for this one, the vertical asymptote, there doesn't appear to be one, right? So there is none for a vertical asymptote. Horizontal, it does look like the number 1 in, see, it's right there. See our vertical shift there, that +1. So our horizontal asymptote is y equals 1. There are no holes. There's nothing wrong with this function because there's no x in the denominator. The domain is going to be -infinity to infinity. It just goes on forever. The range is going to be from 1 to infinity because your asymptote is right here at 1. All right, and your end behavior is going to be as x approaches infinity, y approaches infinity. No, I'm sorry. It approaches 1. And as x approaches -infinity, y approaches infinity. Okay. And that should be good for that one. So domain and range is important for this question, as well as being able to answer these. So here's what happens. I know I did this super quick in class. Here's what you're going to want to do for these. For functions that have, the ability to be factored, we're going to want to factor each one of these. And the reason is we're looking for a major problem or just kind of like a minor problem. So what's a major problem? Well, look at when I factored this. I factored the numerator factored to be x plus 2, x plus 3. X times x is x squared. Then we get 3x and 2x as my middle terms. And then 2 times 3 is 6. So that's my 6 right there. The denominator I factored out of 2, which gave me x squared minus 1x minus 6. And then after I factored that, I factored it into -3 and +2. So x times x is x squared. X times 2x, 2 is 2x. Minus 3x, that gives me my -1x that's there. And then -3 times 2 is -6. What I did here was I crossed out something that was similar in the numerator and the denominator. And the reason why is that's what we're going to call, that's what we identify as a hole in the graph. What happens is x plus 2 over x plus 2 is the number 1, right? But it's not the number 1 because we can't divide, the only number where this doesn't work, and I did that, I set it equal to 0, and I solved, is at -2. So the result here is that we have a problem at -2. -2 works here. See, it works here, it works here, it works here, it works here. It doesn't work here. However, because there's an x plus 2 in the numerator, it's a small hiccup. It's a small little mistake that the graph has. And that's what we refer to as a hole. Okay, so the hole is at x equals -2. And the thing is, because there's no output, we normally refer to wholes. I know I put 0, -2, but we don't know if that's, I'm sorry, what did I do? No, I wrote this wrong. We're not going to refer to it like that. We're going to say the whole happens at -2. Now, if I asked you what its output could be, what I could do is I could ignore what's there, literally, and just work with x plus 3 over 2 times x minus 3. And just say what would happen at -2. Well, that would give me -1, and it would give me 2 times -5, which actually is -1 over -10, which is a tenth. I think I did that math right. Nope, I did something wrong. -2 plus 3 is a +1, making that a positive, making this a -1/10. Okay? And that's what you see there is what an idea of it where it should be is -1/10, but it's not. So we're not going to do any of that work. So let's just erase all of that. But what I do want to do is say, okay, x equals -2 is the whole for this. So where does the vertical asymptote happen? Well, the vertical asymptote happens at this spot right here. That x minus 3 is my vertical asymptote. Because it doesn't clear with anything in the numerator, we have to be very cautious. This is an infinite problem, not a small little hiccup or gap, an infinite problem because it doesn't clear with anything in the numerator. So at x equals 3, that is my vertical asymptote. Okay, so here's x minus 3. That's our problem. Here's x plus 2. Let me move this down. That's the whole. So x plus 2 equals 0. So notice I'm taking each one of these and setting equal to 0 because at each spot there's a problem. So we see at 3, there's a vertical asymptote. So x equals 3 is my vertical asymptote. So far, so good? All right. Where does a horizontal asymptote happen? This is super cool, too. Let's go. Whoops. Whoa, I didn't know I could do that. I got to figure out how I did that. All right. Where does a horizontal asymptote happen? We're going to have to go all the way to the beginning. Let me ask you, a horizontal asymptote really is kind of like looking at end behavior. So it's saying if I go on and on and on and on forever, where would this function tend to lean towards? So if I have $1 billion, $1 really is not going to make a difference. It's not going to make or break me. And if I have -1 billion, if I'm that far in debt, who really cares about $1 or $2? What I'm trying to say here is don't worry necessarily about this or about this. So don't worry about the things that are being added or subtracted on a smaller scale. Look at your big picture. What's your big picture? These are the big picture. Whatever's happening in terms of infinity and in terms of negative infinity will happen and will be the most greatly affected by these two items. So let's take a look. What happens when I have infinity squared over 2 infinity squared? Imagine that. So as x approaches infinity, what goes on? Well, let's see. As x approaches infinity, I have this happening. Okay? So imagine I narrowed f of x down to being just x squared over 2x squared. And again, this is how I find a horizontal asymptote. So as x approaches infinity, I have infinity squared over 2 infinity squared. Now you're going to tell me, I know this. This is what I get all the time. Infinity doesn't matter. It goes to infinity. Yes, I know that. But think about the 2 in the denominator. it's multiplying infinity by 2. This is crazy to say, very crazy. This grows faster. It's double this. And let me tell you why. What is 100 squared? It's 10,000. What's 100 squared times 2? It's 20,000. So it's always going to be double what's in the numerator. So when I simplify this, I get 1 over 2. So that is what happens as x approaches infinity. Let's see what happens as x approaches negative infinity. I get negative infinity squared over 2 times negative infinity squared. Well, that's the same as saying infinity squared over 2 infinity squared, because a negative times a negative is a positive. Again, it's 1/2 as x approaches negative infinity. So what I just found is what we call a horizontal asymptote. It's 1/2. So our horizontal asymptote is y equals 1/2. We write it as y equals. We'll take a look. What looks like is happening right here? 1/2. That's why, because as we go on forever in both directions, it gets closer to 1/2. So with all of this said, the domain is all real numbers except for, it's all real numbers except for what number? Well, 3. That's where the vertical asymptote happens. See, isn't this cool? Everything, all the work we did is helping us to figure out the domain and range. So what's the range? Well, it's, oh, did I use that color anywhere? No, okay. The range is negative infinity, negative infinity, all the way up to 1/2, and 1/2 to infinity. There we go. So what's end behavior? Well, end behavior as x approaches infinity and as x approaches negative infinity, y approaches 1/2 and y approaches 1/2. So it doesn't matter which one I'm approaching. Now notice this doesn't come from the domain and range because it is focusing in on that horizontal asymptote. It's really just, well, I mean, it is coming from the range, so. And only the range. All right, good. All right, this next one. This one I can already tell visually doesn't have holes according to the visual, but I'm going to check. So I'm going to factor this one. Let me do everything right. So the factoring, I'll do in purple again. I'll do the factoring is x minus 3, x plus 1 over x plus 3, x minus 2. Let me double check my work. X squared plus x minus 3, it's my negative 2. Minus 3 is, there we go. Okay, x times x is x squared. Minus 2 plus 3, that's my positive 1x, minus 6. All right, so what do we got for issue? Well, I have no holes, right? Holes, there are none because there's nothing I can do. There's none, I can't simplify any of these out. What are my vertical asymptotes? Well, I did that in green. So x plus 3 equals 0, so x equals negative 3, and x minus 2 equals 0, and so x equals 2, so these are my vertical asymptotes. So x equals negative 3, x equals 2. And we see them right here, negative 3 and 2. All right, what's my horizontal asymptote? Well, I did that again. Horizontal asymptote is in blue. Okay, it looks like the number 1. Let's see if it really is. Ignore this junk. Let's take these, and what do you think? What do we think? Infinity squared over infinity squared? I think that looks like 1. And I think negative infinity squared over negative infinity squared is the same as infinity squared over infinity squared, which I think is 1. So I'm thinking my horizontal asymptotes are just 1. Well, in this case, just 1. So y equals 1 is my answer. The domain is going to be in purple here, so it's going to be all the numbers, so negative infinity to negative 3, negative 3 to 2, 2 to infinity. So it's at all the vertical points, all the vertical breaking points. And the horizontal asymptote is the range is going to be based on the horizontal asymptote, negative infinity to 1, and 1 to infinity. And my end behavior is going to be as x approaches infinity and negative infinity, y approaches my asymptote, my horizontal one, which is 1. And that's it. Now again, take a look. Look at, that's a horizontal, here's a horizontal asymptote. It's crossed, right? So horizontal ones can get crossed. It's just about them approaching it at the end. All right, and I think that's it. So for these, again, you're just going to go through, you're going to find the vertical. I don't know if the answer key has all, oh yeah, the answer key has all of them. So you're just going to go through and solve these. So, you know, the first thing you'll do, I think I'm going to factor out a x minus 2 and a negative 2, and I'll get x squared minus 4. And don't forget, this will factor into x plus 2, x minus 2 over x minus 2. So here we go. There's a hole right there. So a hole happens when x minus 2 equals 0. So x equals 2. That's the hole that I have. This is going to be, what's my vertical asymptote? It's what I did in dark green. So this is my, that's not a good color. You know what, I'll do this color. So x plus 2. So the vertical asymptote is going to be x plus 2 equals 0. So x equals negative 2. That's my vertical asymptote. Okay, my horizontal asymptote is going to be when I circle these. Okay, interesting. I get x over negative 2 x squared. So it's going to be infinity over negative 2 infinity squared, which is the same as saying infinity. No. Let me get rid of infinities here. You know what I should be doing is the approximate symbol, because we can never get to infinity. I'm just kind of trying to figure out what it could possibly be. So 1 over negative 2 infinity, which is going to actually go to negative infinity. What's 1 over infinity? It's like saying 1 over a billion. It's about 0, right? So that's going to be about 0. And the same thing's going to happen with this other one. So it's going to also be negative infinity over negative 2 negative infinity squared, which is going to be about negative infinity over negative 2. Negative infinity times negative infinity is infinity squared. And then this is going to be about infinity over 2 infinity squared, which ends up being about 1 over 2 infinity, which ends up being 1 over infinity, which ends up being about, 0. So for all of that work, I get a horizontal asymptote is is y equals 0. Right? Let's see what our answers are. So 2 for the whole is at 2, x equals 2. The horizontal asymptote is at 0. The vertical asymptote is at -2. Domain is all real numbers except -2 and 2. And you can just write that one out like you normally would. Okay, so do some of this practice in class tomorrow or at home tomorrow, but I'll go over any questions that you might have. All right, good luck.